So for the group A students, from 2 to 2:30, there will be a doubt clearing class for both biology and mechanics at room number 123. Okay? Group A. Okay? Doubt clearing class for both biology and mechanics at 1 to 3 at 2 p.m. Okay?
Huh? So, Tanmay will take a doubt clearing class at 1 to 3 for group A from 2 to 2:30. He will be there. If you have any doubt, you can come to him. And I'll be there anyway at Alladi after lunch, so you can come to me also. Anyone interested, group A. So, okay? Group, oh, sorry, my group is group B, so, sorry, group B, okay?
Go on. Can I start? Hello. Can everyone hear me? Can everyone hear me? No. It's on. Can everyone hear me? How did you know I was asking? Yeah. Hello. Can everyone hear me? Yes, no, maybe. You can't hear what I'm saying. Can you hear what I'm saying? Yes or no? Okay, thank you. Jeez. Okay, don't worry about torque. The future of democracy does not depend on you understanding the difference between force and torque. You know Newton's laws, that's a pretty big deal, so don't worry. This is going to be the second talk on the history of science. By the way, thank you all for submitting your feedback forms without listening to my second talk. I look forward to what you have to say. Yeah, so but before we begin, were there any questions from yesterday? I didn't receive any at all. Like 0 questions. You're very kind. Okay, fine. So let's begin, right? So the plan for today will be to, excuse me? No. So the plan for today will be to discuss what is called wave-particle duality, and like basically we want to understand whether light is a wave or a particle. And what? See, yeah, no, I'm. That's roughly correct. Thank you for that contribution. But I'd like to go over the history, like I said, right? And also I'd like to talk about more importantly, this talk we'll try to answer the question. Well, not try to answer, but suggest possibilities for what the word scientific really means. So let's see how this goes. This story, you all know this actually. Our story begins with Isaac Newton, who suggested that light was made up of particles, right? And he called them corpuscles. I don't really know why, because it's a strange word. But he assumed that these are rigid, massless, and elastic objects. And he was able to explain reflection using this, right? And it was a bit awkward, but he was also able to explain refraction. Does everyone know what refraction is? Yes. What is refraction? Bending of light when, that's correct. Yeah, that sounds right. It's bending of light when it enters a different medium, right? So if water goes, that's why you can't see in water, right? Because you can't see clearly because the inside your eye, the vitreous humor, never mind. But yeah, you can't see clearly in water. So Newton supposed that they were particles, and Newton was a very influential man, but he was also a very nasty man, which means every time someone said he was wrong, he got very upset and then basically shut them up, right? He's had a history of doing this, and he's a very entertaining character actually. Huygens was one of the people who defied him. he came up with the wave theory of light. He didn't actually come up with it. The wave theory of light was first introduced by René Descartes. Have we heard of him? What do we know him as famous for? Cartesian plane, yes, Cartesian coordinates. René Descartes was also a very influential philosopher, and he introduced the wave theory of light, and Huygens developed it. So, does everyone know this? Is there a pointer, by the way? Pointer? No. Check one minute. Ilya. So Huygens introduced this concept of secondary wavelets, right? Which is basically every point on a wavefront. Do you guys know this? You guys have read this, right? No. Okay. So what are waves? Waves are things that do this, right? Okay. So yeah, it's like an oscillator except it's moving, so it's like a wave. Okay. So what Huygens said was that. Okay, so if you know what a wave is, you know what a wave front is. When you go to the beach, for example, you see like this huge parallel crest coming towards the beach, right? And then it comes and then it hits the beach. So this long parallel, that's called a wave front, right? It's the point of, like technically it is defined as the point where all the phases are the same or something like that. The definition doesn't matter. Just keep in mind this beach analogy, right? Now, all the points on the wave front, which is the blue line, right, in the first diagram, all of them generate small circular waves of their own, right? And the future wavefront is just a tangent to all of these circles. That was his idea, right? So, for example, you can see that light. So if each point. So one of the questions they had was, if I turn on a light in a room, the light spreads out, spherically, right? Like the intensity varies with distance. It doesn't vary with direction. So it's isotropic is what they call. So one question was, if it was a wave and if it was a spherical wave, how do you explain linear propagation of light, right? Light travels in straight lines. So this is how you do it, right? So you just assume that your future wavefront is always the tangent to all of the circles. And the same thing is true even of spherical waves. Right? Ripples in a pond, you can explain them using the same thing. Right? You drop a stone in a pond and then the waves come out, and that's what ripples look like. Right? So that was Huygens, and Huygens' theory was very good. It was a very good theory, but again, Newton was a very influential man, and because he was Newton, and he didn't like being wrong. So no one really took Huygens very seriously. Some people did, right? Very important mathematicians took Huygens very seriously, but a lot of people didn't take it very seriously until the double slit experiment. You must have seen this in school, some of you. Young's double slit experiment. It's a very famous experiment. Can someone tell me what happened? What they did? Wait, I don't know what an electron is yet, right? No idea. Tell me. Yes. Yes.
Monochromatic source of light.
Okay.
And then there's few slits.
Okay.
Such that it is smaller than the wavelength.
Okay. That's just a detail, but okay. Yeah.
Then there was the screen. What happened was the intensity of light was too bright at certain spots and it became very dark.
Okay. So there was an interference pattern, right? So dark light, dark light, dark light. Yeah. So that's one of the things about waves is that waves can either add up or cancel out, right? We know this. We know this to be true. So this is actually a diagram from Young's notebooks, and so this is how he described the interference pattern. He said, you have two sources of light, and they're both emitting waves, and there is an interference pattern that you can see at the end on the screen. Right? Now, this is something that cannot be explained using a particle model of light. Only waves have the property of interference, right? And this is important to remember. Waves interfere. That's one characteristic property of a wave. So keep that in mind because that will be important in the future. So the double slit experiment sounded the death bell for the particle model, right? No more particles, only waves. Fine. Everything's going well so far. And it got even better when does everyone know who this man is? James Maxwell? Right. Okay, so this is a very scary slide because there's a not very friendly looking man and 4 equations with symbols you don't understand. But let me explain. Maxwell is a guy who came along and said, look, you guys did a lot of experiments with electricity in the labs, right? You saw magnetism and so on. So what he came along and said was that you look at electricity, magnetism, and light, right? You must do experiments with light, refraction experiments and things like that in your labs. What he said is that I can explain all of these things using just these 4 equations. Now, what these equations say, it is important, but at this stage, I'm not going to try and explain it to you because it takes some time. But it's safe to say that if you're going to do a bachelor's in science, for example, you will understand what these equations mean, right? So, what these equations, they're a very powerful set of equations. It's just 4 equations, and it explains every known phenomenon at the time relating to electricity, magnetism, and light, right? So it's very important. And also another thing to note is that you can see that time varying, and you saw this in your experiments, time varying magnetic fields generate electric fields, and time varying electric fields generate magnetic fields, right? You saw this when you looked at the motor, right? There is a change. How does a motor work? There's a changing magnetic flux. It generates a current, EMF. Yeah. They saw this, right, in the labs. Janu? Wait, no, you were geometry. Okay, fine. No, but you did see this, right? So these were very important set of equations, and in fact, it's the dream of every graduate student to come up with a nice set of equations like this that explain a lot of things, right? Hasn't happened since then, but okay. One can hope. So what these equations also tell you is that light, right, electromagnetic radiation. The reason we call it electromagnetic radiation is because of these equations. These equations tell you that light is nothing but a fluctuating electric and magnetic field. Visible light, ultraviolet light, infrared light, all of these are just electric and magnetic fields, oscillating electric and magnetic fields. So this is a very important set of equations. Yes?
What does E stand for? Is it electric field?
E is electric field, B is magnetic field. Yeah, and the inverted triangles and the Greek letters are all, the inverted triangles are like derivatives of some sort, right? You learned about, sorry? Yeah, it's not an ordinary derivative. It's a kind of like fancy derivative. No, the inverted triangles, right? Those are like a fancy derivative, right? It's not an ordinary derivative. It's a fancy derivative. And the Greek symbols are properties of vacuum, properties of materials, for example. Yes, that's correct. J is a current, right? No. Okay, well, I think I'm just going to move on from this slide because it's making me uncomfortable. But you don't need to know what these equations mean. The point is that it tells us 2 things. One, light is electric and magnetic fields, right? They're the same thing. And also that these equations explain everything about electromagnetism at the time they were written down, every single thing, right? Now, also at the same time, the atomic theory was becoming more and more important, and chemists were, in fact, like in physics, we don't like to give chemists too much credit, but they were actually quite smart. So they had laws about mass conservation in their experiments, and laws of definite proportion, and Mendeleev came up with the periodic table and so on. So all of these suggested strongly that there was an atomic theory somewhere underneath, right? And you must have studied all of these, like the law of definite proportions and the periodic table. You've seen the periodic table? All the elements arranged, yeah, okay. Also at the same time, there was Thomson and his cathode ray experiments. You've seen this also? You've seen this also, okay. So what is quite surprising about these experiments is that until then people thought electricity was a fluid. They thought, yeah, I know it's impossible to imagine today, but back then they thought electricity was some sort of fluid, and it was flowing through wires and things like that. And if in fact electricity was a kind of fluid, then you shouldn't have any non-trivial behavior inside a cathode ray tube, because in principle the resistance of vacuum should be infinite if it was a fluid, right? But you did see non-trivial results in cathode ray tube experiments. And that's really where the electron comes from, right? Thomson hypothesized that there was a particle. Sorry? You said something. What? Oh, an electron gas. Yeah. Well, yeah. So that's where the electron comes. It's a particle that carries electric charge, and the moving electric charges constitute currents, right? So there were also some problems with the theory of radiation. Radiation is when you heat up like a piece of metal, for example, right? It emits light, right, of various wavelengths, right? And that's roughly what it should look like. Yeah. So for example, it's not very clear, but this is wavelength. The x-axis is wavelength, and as you get hotter, the wavelength becomes smaller, right? What does that tell you? That means when you start heating a metal, it starts with red, and then it slowly goes over to blue and so on, right? So there were problems with the theory of radiation because there was no theoretical understanding of how to get. So these curves they knew about, but there was no theoretical understanding of how to start with first principles and derive the equation of this curve, right? But and I won't go into them because they're slightly complicated. But let me just say that Max Planck did an extraordinary piece of work where he hypothesized that all electromagnetic radiation, all light, comes in discrete units called quanta. Right? They're called quanta. Quantum, you must have seen Quantum of Solace, the movie, James Bond movie. It's the same word, right? But it just means a discrete unit, right? And so what he supposed, until then people thought light was just a continuous thing, it just kept coming, right? But no, what he said was that light comes in discrete units called quanta, right? And also Einstein came along and then talked about the photoelectric effect. Have you seen this? Some of you have seen this. Okay, the photoelectric effect is basically you take a piece of metal again, and then you shine X-rays on it, right? And what you observe is that electrons come out. Electrons are shot out of the metal. And this was an important experiment because if you assume that light was a wave, you couldn't explain what was happening, right? So we thought that we were safe and clear because the double slit experiment showed conclusively that light was a wave, right? But now we have another experiment, the photoelectric effect, which cannot be explained using the wave theory, right? It turns out you can explain it using a particle model, which is what Einstein did and which is what he won his Nobel Prize for. But the photoelectric effects message was quite clear, which is that light comes in discrete units. Quantum of they come in quanta, right? Now de Broglie, which was he French? He was French. Yeah, French. He was a French. He was a prince actually, Prince de Broglie, and he postulated that all matter, not just light, but all matter had wave-like characteristics. Right? That was the lesson he learned from the photoelectric effect, and it was a very, very important step. I mean, as far as I know, he didn't do much else in physics, but the fact that he said this was fairly important. And you must have seen the formula also that like the wavelength of a matter wave is inversely proportional to the momentum, right? Which means heavier objects, right? Heavier objects have very small de Broglie wavelengths, and lighter objects have much larger de Broglie wavelengths, right? So if de Broglie was right, we already have like not recently, or like in the late 19th century, Thomson was doing his experiments and he had found particles that carry charge, right? Very, very small, very light particles that carry charge, right? So they should have some sort of wave behavior, right? Because they're very light, and if it's very light and it's inverse as the momentum, then it should be that the wavelength is very large, and if the wavelength is large, then these waves can interfere, and then we can see interference patterns. This is exactly what they thought, and they went on to perform a wonderful experiment. It's called the Davison and Germer experiment, where they took electrons, and they were able to show that electrons can be made to display diffraction patterns. Just like in the double slit experiment, where you had light, dark, light, dark, light, dark. Electrons do the exact same thing. which is quite shocking because it's telling you something very fundamental about matter and radiation. It says both of them have both wave and particle characteristics, right? In fact, in 1999, they were able to show that, do you guys know about Buckminster fullerene? It's a very big molecule. It's about it's like a ball, yes, and it has like 60 carbon atoms, so it's fairly heavy, right? And what they were able to show is that even these guys show interference patterns, right? So I guess the message really is that matter does have both wave and particle characteristics, and this is fully understood within the scope of a subject that everyone has to learn here at IMSC. At least if you're doing physics, it's called quantum mechanics, and quantum mechanics is a tremendously successful theory. It and its generalizations have been responsible for the meat of scientific achievement in physics in the last throughout the 20th century. So yeah, hopefully one day we'll talk to you about that also. But now what I'd like to do is I'd like to go on to what the question of what scientific means. What does the word scientific mean? Because there are a lot of questions, right? For example, let's say that I suggested to you that the reason that if I jump up, I come back down, the reason I do this is because there are strings tied to my feet, and these strings are elastic strings. So if I jump high, then like they pull me back down. Now, is this scientific? Does this sound scientific? No, right? Why? Because there are no strings, right? No strings. What if I said they're invisible strings? No, so you see why this might be a relevant question. You can say whatever you want about reality. Question: So we have a problem of demarcation. How do we say that a certain assertion is a scientific one and other assertions are not? This is an important problem. At least it was still remains a problem in philosophy. Is the question of how to distinguish between scientific and unscientific methods of inquiry or hypotheses, right? Now, Karl Popper was a very famous philosopher of science, and he realized, and once I say it, this will sound very obvious to you, but people had not stumbled upon it at the time. Popper realized that you can have 1,000 experiments that will confirm your theory, right? But if you have a single experiment that it doesn't work with, right? If you have a single experiment that does not fit your theory, it's wrong, right? This is the whole issue. You have on one hand you have verification. You'd like to verify your theory, but there is really no way to do that because you cannot perform all possible experiments. You cannot conceive of all possible experiments. What you should look for is a way to show that your ideas are wrong, right? That's what falsifiability means. It means the ability to show that a certain idea or assertion is incorrect, right? And what Popper suggested was that an idea is scientific if it is falsifiable. He was drawing a line in the sand. He said, if it is possible to show that your idea is wrong, then it is scientific. If it is not possible to show that your idea is wrong, then it's unscientific, right? Take a moment to think about this. What he's doing is not really talking about physics or chemistry or biology. What he's talking about is what science is, right? I'm not saying I know the answer. I'm not saying he got the right answer, right? And this is a question that you'll have to ask. Sorry? Well, it's not common sense either, is it? I mean, like, well, if it was common sense, then Aristotle would have said it, but he didn't. This sort of thing takes time, right? So you have to understand the distinction between verification and falsifiability. Doesn't matter what your name is or who your father is or how much money you have. If you suggest a theory and there's an experiment they do tomorrow that shows that it's wrong, it's wrong. That's it. Doesn't matter, right? Falsifiability is Popper's criterion for what a scientific assertion is, right? Now, yes. Okay, so I didn't want to. Yeah, I don't know why I put that in there. But Popper was actually working on the idea that how you discard of scientific hypotheses is a bit like natural selection, evolution, right? Which is, PS1 is like you have a possible scenario, right? You have some experimental observation that is made, right? And someone comes and gives it to you. Let's say I have an experiment and I have the data, right? And I give it to each and every one of you. I give you a copy of the data, right? Now, there are certain regular structures in this data. There are certain patterns in the data. Now, I ask each of you to come up with a possible explanation for why that pattern exists. And each of you most likely will come up with your own idea. Or you can work in groups and you can come up with ideas as groups. Doesn't matter. But there will be a lot of ideas, right? Now, EE1, I think stands for error elimination, right? Which is, you have, so T is, what is TT? What is TT? Testable theories, or yeah. I don't really know what these expand to. I did, but I've forgotten at the moment. Basic idea is everyone comes back with a guess for what the actual theory, underlying theory might be. No. So let me explain. It's not composite. Each of you comes back with a guess as to what the possible explanation would be, right? Now, all of you have guesses, right? How do we decide whose is correct? Test it out, yeah, but we have to do different experiments, right? So we keep doing different experiments, and in some experiments, some of your theories will be incorrect, right? That's just how it happens. Like all of your guesses, unless you all came back with the exact same theory, right? What will happen is, there will be some experiments for which your theories don't work, right? So you throw away those, right? So really, how you're progressing from left to right in this equation is it's a form of fitness. How fit is your theory to incorporate new tests, right? That is the sense in which it is parallel to like evolution or natural selection. Now, once you've done the error elimination, then you have a theory. You have a theory, and then you go on to do new experiments and you find a possible scenario too. So this whole process repeats itself over and over again, right? Now, Thomas Kuhn was a very famous historian of science, and he wrote a wonderful book titled The Structure of Scientific Revolutions. I'd like to tell you about this because a lot of people believe that this is how science happens, right? You don't have to believe it, and I will suggest alternatives, but he had one idea for how science actually happens. So the word paradigm was introduced by Kuhn in the scientific context to describe model problems and solutions. Let's take Newtonian mechanics, for example, right? Can you give me examples of standard problems in Newtonian mechanics? F equals ma problems. Projectile motion, right? That's like, this is a problem that everyone has to understand, right? What else? Simple pendulum. You study the simple pendulum? Give me guesses, come on. I'm telling you what the theory is. I'm telling you that the theory's fundamental equation is F equals ma, Newton's laws, right? Now give me examples of problems that you see in your textbooks or that you've had explained over the last few mechanics lectures. Okay. Can you give me examples of standard problems? Okay. So inclined plane problems, right? Those are also standard, right? Ball is dropped from a height. Yeah, that's part of the projectile motion problem because this is just like no angle. Conservation of momentum is a concept. That's true, right? But so all of these ideas, right, can be said to constitute a paradigm. It basically gives you, it's a prescription for how to go about solving problems, right? If I give you a new problem, you know how to solve all these old problems, and you know all these rules: conservation of energy, conservation of momentum. You know all these rules. You can apply these rules to your problem, and you can try to get an answer. That's what a paradigm is, right? Now, Kuhn identified normal science in the following way. What he said was that all scientific activity, right, within a paradigm is just puzzle solving. You have a set of rules, right, and you know how to apply them, and you have a problem that has not been solved. So what do? You go ahead and apply those rules to the problem, right? It's just like if I gave you a problem in Newtonian mechanics, I just imagined a problem one day and I gave it to you, you would be doing normal science. You're trying to find a solution to a problem that has not been solved using established techniques, right? So what he said was that all normal science is just puzzle solving, right? And what does puzzle solving help you do, right? Puzzle solving helps you acquire details within the paradigm. It helps you test various limits of the thing and so on, right? So it just helps you learn more about this paradigm, this structure itself, right? And most normal science usually does not involve questioning the foundations or underlying assumptions of the theory. Like if I gave you a very strange inclined plane problem, you're not going to start thinking about what mass is or what friction is. That's not what I want you to do. That's certainly not what your school teachers want you to do, right? Because if you start thinking about what mass is when they ask you to solve a pendulum problem, then you'll be there all day, right? So that's not what you're expected to do, right? So there's no questioning of the foundations or the underlying assumptions. But here's the problem. What if you keep doing this for a long time, again and again and again, you keep puzzle solving, and once in a while you will hit upon a problem that the answer doesn't make sense. All the rules, everything that you know just doesn't work on this problem, right? What do you do if something doesn't fit? That's essentially the question, right? In this case, Thomas Kuhn calls these anomalies, right? It is a failure of the paradigm to take into account observations from experiments or theoretical models. It is a failure of this earlier worldview to incorporate these facts, right? It just doesn't happen, right? Now, most anomalies are solved sooner or later. Let's say, for example, that you were given a homework problem by Partha and you weren't able to solve it. And you think, or you did get an answer and the answer doesn't make sense. And then you say, oh my God, I found an anomaly, right? This is wrong. Newtonian mechanics something is wrong. Most cases, what has happened is you've misunderstood something, most of the time, right? Or there is some trivial modification you can make or some new concept you can learn that will allow you to solve the problem, right? So most anomalies are not really anomalies, right? They can be understood within the theory itself. However, some of these will expose very, very big weaknesses in the foundations of the earlier theoretical structure, right? For example, if you look at classical electromagnetism, this whole wave particle thing would be a very good example of something that exposes weaknesses in the foundations, right? Classical mechanics it just stops working, right? After a point it stops working because electrons diffract, but you know that electrons are particles. So how should particles diffract in the Newtonian? It just doesn't make sense, right? So this is a very stark weakness in the theory itself. So a huge part of science, and this happens once in a while, it doesn't happen every day, certainly, is a huge part is just recognizing that a crisis exists, right? This happened, for example, when Copernicus came up with his heliocentric model of the solar system, right? So because before that, what they believed, Ptolemy told them that the Earth is at the center and the sun and all the stars move around it, right? The problem is, it's a cute theory, right? But the problem is it's very awkward because if you want to explain how the planets move, then you have to introduce circles within circles, and they're called epicycles. And you were able to make very accurate predictions, right? They were able to tell you where Venus was at a certain time and date and so on. But it's a very awkward theory. But once you assume that the sun is at the center, then things get much simpler, right? Once you stop insisting that all your orbits are circles and you allow for ellipses, for example, then things get much easier, right? So the Copernican revolution was one example of a place where crises were developing, right? And what do you do when you have a crisis, right? That's when revolutionary science begins. And what revolutionary science is, in the sense of Kuhn, is to explore alternatives to the old paradigm. It is to re-examine the foundations of your theory and try to understand what is wrong with it, right? Why isn't it working in these cases, right? And revolutionary science is a very entertaining time, at least for science historians, right? We saw yesterday that the founding of molecular biology as a subject and the founding of its principles was a period of high drama. There was a lot of tension, a lot of disagreement, a lot of just anger, in most cases. And revolutionary science, the way it goes is that there is a lot of disagreement, there's a lot of tension between the parties involved, a lot of people have a lot of different ideas, and any of these new ideas that might work it takes a long time to accept. And that's how it should be. right? Sometimes people say, oh, you know, they don't believe me when I tell them that this is how things are, and so on. Or for example, like some graduate student will go to a conference and he'll present his work, and then people will criticize it, right? And then he comes back and he feels sad. He's like, oh, they didn't think it was awesome, and I thought it was awesome. That's how it should be. You have to have very high standards for what you accept as good work and so on, right? So if one of these guesses, one of these reimaginings of the foundations is consolidated and developed, and it does in fact incorporate these old, what did I call them? These old anomalies into it, and is able to explain these anomalies, then what Kuhn said is that you have a paradigm shift. Right? You had one worldview, and then it was not able to explain certain things, and as a result, you worked very hard, and you found that there is a different worldview. Right? So this is, for example, in the classical mechanics, classical world and the quantum world. Right? This was a very important paradigm shift in the 20th century. Right? And once the paradigm is shifted, it's back to normal science. Right? Ever since quantum mechanics was developed in the 1920s, we've been doing normal science. Right? There have been developments, but the fundamental principles of quantum mechanics have stayed the same. Right? So then it's back to normal science. I should say at this point that now all of you are thinking, I'm going to do revolutionary science, I'm not just going to do normal science, right? If you are interested in science. The thing is, like, it's not clear when a revolution is going to happen. Right? And when I say normal versus revolutionary, I'm not saying it, I'm not calling it normal because I think it's any less important. You need both kinds. Right? If everyone was trying to do revolutionary work, no work would get done. Right? The same way, if everyone was doing normal science, the frontiers of your theory would not be pushed. Right? So you need both. So how many of you think that this is a good model for how scientific revolutions happen? How many of you think it's reasonably accurate? You can raise your hands. It's fine. Yes? Some of you have reservations. Okay. Well, the good news is that you're not the only ones. There have been a lot of disagreement regarding this, and these are some names. I didn't want to go into the details because they're fairly involved. So Paul Feyerabend, Imre Lakatos, and Stephen Toulmin. You can Google these guys when you get back home and maybe read some of their essays. Some of them are fairly accessible. And if you are interested in this sort of thought, so one of the reasons I decided to do history and this last bit, like philosophy of science, is because I actually wanted to be a philosopher when I was young, but then I wasn't good enough, so I started to do physics. But anyway, so these are some guys who disagree fundamentally with what Thomas Kuhn suggested was the structure of scientific revolutions. So you can take a look at Feyerabend. So Feyerabend, for example, has a very entertaining point of view. He pioneers what is called epistemological anarchism, right? Which is a nice big word. You can impress your friends with it. But what it means is that he's essentially saying there is no such thing as the scientific method. What you call the scientific method is just whatever works at the time, right? You have a problem, you do whatever you can to solve it, and then later you call it scientific method. Fine, right? That's what he said, in a nutshell, right? Of course, you have to read it to understand it better. Lakatos developed what was called the research program methodology, right? So he thought that there were like a lot of competing research programs, and that one of them would succeed in the end, and so on. And Stephen Toulmin does not agree that science is ever revolutionary. Rather, he says it is an evolutionary process, right? Evolutionary in the sense of Darwin, right? So this is, I think, the end of my talk. I wanted to, do you have any questions at this point? Yeah, that seems to be the case. Since you don't have questions, this is a good point to give you homework. I know maybe you're not really going to do it, but I recommend these two books, Charles Darwin's The Voyage. I recommended to a couple of you Origin of the Species. Maybe not such a good idea, right? But Charles Darwin's The Voyage of the Beagle is a very entertaining book. It's like a travel book, you know? So he traveled all around the world, and he was collecting samples, and he was meeting new cultures and things like that. Sorry? Galapagos, yes, the islands, yes. So he traveled to a whole lot of places, and he wrote about these journeys in a book called The Voyage of the Beagle, which I encourage all of you to read. It's a very entertaining book, and Darwin is just very cute when he writes. You just want to give him a hug. So that's nice. And James Watson's The Double Helix is also a very entertaining book. I mentioned yesterday that it's really a very unique perspective into how science happens. So that would be the end of my talk. Thank you very much. And if you have any questions, please feel free to approach me later. Notes might take some time. Like, I'm still writing them. I'd like them to be a little more comprehensive than the talks themselves, and I'd like for there to be more references. So in the meantime, if you have any questions, please feel free to email me. I think my email is probably somewhere. Yeah, okay. So if you'd like to contact me, if you want recommendations or papers or something like that, please let me know, and I'll be happy to give them to you.
So for the group